Okay, so if we take a look at 39, I know you don't need to do the entire 39, but let's talk about 39. 39 said that it's from 1998 to 2003. All right, and they gave us f of x is equal to, oh no, I lied. I was looking at the wrong one. Hang on. Let's back up the bus here. 1980 to 2000, and they give us the function f of x is equal to 0.10x plus 2.75, right? And what we are measuring is the average price of a movie ticket from 1980 to 2000. Okay, so that's the information they're telling us. All right, they said it says graph the function, identify domain and range. Okay. So when I do this L, my X is my number of years since 1980, but it only goes up to 2000. All right, so what I'm going to need to do is, because L, I have an end date, I definitely have to use that as one of my numbers. So be very crafty about what numbers you're using. I definitely want to know the number of tickets in 1980 because that's my y-intercept. I definitely want to know, well, that's 20 years later. I definitely want to know the number of tickets 20 years later because that is my end one, and maybe I'll do like another one in between. Maybe I'll do 10 years since 1980. All right, so if I put those in, f of 0 is going to equal $2.75. And you may have different values in. I'm not saying these are the values you have to put in necessarily. All right, but because they give us a start year and an end year, I at least have to use those 2 years because it gives me my start value, cost of tickets, and my end cost of tickets, and then one in between. So that's going to be 10 is equal to 0.10 times 10 plus 2.75. So this is going to be 0.1 plus 2.75. So f of 10 is going to be 2.85. So this is 2.85. All right, if I put 20 in, I get 0.10. No, I lied. This is going to be 1 plus 2.75, which gives me 3.75. Going too fast. So I have 0.10 times 20 plus 2.75. Well, that's going to end up being, if I multiply by 10 first, that takes us to 1, and then by 2, I get a 2, right? I'm adding 2 to it, right? Did I do that mentally right in my head? Okay, so this is 2 plus 2.75, so this gives me 4.75. So here's 4.75. So without graphing this, because I think you guys all know how to graph it, does anybody want me to graph this? Okay, so L, for me to graph this, we would use these, okay? But for my domain values have to start at 0 and end at 20. All right, so for my domain, it's 0 is less than or equal to x, which is less than or equal to 20 years since 1980. But since that's my domain, my range values have to use the coordinate pair partner y to go with it, which means my range has to be 2.75 is less than or equal to y, which is less than or equal to 4.75, and this is dollars per ticket. Because that 0 goes with the 2.75, that 20 goes with the 4.75. Does that make sense? Awesome. Does that answer your question? Excellent. All right, what else can I do for you guys? You guys, yes? 40, yep. So I need you guys being like taking the time while you're writing your your givens down, while you're thinking about and analyzing, okay, what numbers do I need to put in for my X values? All right, so don't be so random putting them in, be very thoughtful. All right, so in 40, we have f of x is equal to 4,250x plus 330. Well, f of x is the number of DVD players in thousands. So what this really means is 4,250,000 DVDs. So you would put 3 zeros on the end of that, which really actually means 4,250,000. All right, so keep in mind that's what that means. All right, and X is this is the years from 1998 to 2003. All right, so they're saying graph and identify. Okay, so I need to identify the range and domain. Okay, so Carmen, I'm going to do the same thing here. When I go to make my table of values, well, first of all, I'm going to use 0 because that is in 1998. 2003, that is 5 years later, right? So I'm definitely going to use 5. And then I might do one in between. Maybe I'll just use 1 just to give me another one. I would do 3 points just to make sure you did them right. All right, and then Carmen, I would go ahead and evaluate that function for those. Are you cool with that? All right, do you want me to finish anything else on this? Well, the graph is this, honey. So if I take a look at the graph, let's talk about the graph. So when I have 0 years since 1998, my coordinate point is going to be 330. So I have 0, 330. All right, so technically I probably would have graphed that a little bit more closely than they did in there so I can actually see where 330 is. All right, and then when I put 5 in there, that coincides, Carmen, with that point there for 5 years. And then we would find one more in between to kind of give us a third one. Okay? So again, I need you guys to be super thoughtful about what numbers you put in for your domain values so it gives you your full graph. Always put the beginning, your beginning X value in of where it's going to start. Typically that's going to be 0. All right. Then if you have an end date, always put that end date in. If you don't, like in 40, there is no end. You know, X was just the number of hours that somebody is skating for. So at that one, I would just do 0, 1, 2, 3. Ladies in my back. Are you guys good with that? Okay, so be very thoughtful. Yes? Where your domain is going to be, because it keeps going, it just says the distance traveled after skating X hours is given by that particular function. Okay, they're not limiting the number of hours they can be skating. So we could be skating 0 hours all the way up through 500 hours. I mean, there's no limit to the number of hours you can be skating. So your domain is X is greater than or equal to 0. I probably would say greater than 0 only because, you know, if you're skating for more than 0 hours, but they have greater than or equal to, okay? And then from there, you find out what your f of x or your range value is at 0 hours, and that's your beginning, and then it just keeps going from there, because there's no limit. Well, that's because exactly what I'll just ask this question. So a problem like number 39, look at 39 up here. because there was a begin date and an end date, that means there's a begin domain and an end domain. There's a begin range and there's an end range. All right, but on 41, there's not an end. There's just a beginning, 0 hours. They didn't say, they could have said the distance if they skated anywhere between 0 and 8 hours, right? They could have said that. Then yours would look something like this, where you have a beginning, you have 0 and 8 as your domain values, and then you have 0 and 80, I think, because it was 10 times, they're going 10 miles per hour, 80 as your range values. So that's why there's an end to it. Does that make sense? Well, you can't write it. Right, so I can't write it. There is no end, there is no maximum it can go. There's only a minimum of 0 hours. After that, there was no maximum they gave you. So you can't write it as a compound with a minimum and a maximum. Because that's essentially what these are. Here's your minimum, here's your maximum. Does that help you? Yes. Yes, so Maggie, can I see yours? Thank you, sir. That one, that was I'll bring it back to you. Okay, so if you guys take a look, this is number 39. All right, there's no data. There are no X values lower than $2.75. And to graph this, your values for your Y's, well, there's no Y values. Their values for your Y's are like 0.1 between each other, right? How many of you guys noticed that? Okay. So because that's the case, I think it'd be nice to be able to count by 0.1 if that's what your numbers went up by. So because I want to count by such a smaller increment, I can do a graph break here. If I started at 2 and I'm counting by ones, you're not going to do a graph break, right? But because I'm starting at 2.75 and I'd like to count by 0.1, right, between each one, then making a graph break would be a really good idea. The time that you do graph breaks is when you have a y-intercept and your slope is positive. It's going up, meaning there are no possible values for your y between your origin and your y-intercept. That's when you can do a graph break. Okay? And like I said, on one like this, where you wanted to count by such a small increment, doing a graph break allows you, thank you, sweetheart, allows you to count by those really small increments. Okay? You're welcome. Okay. Are there any other questions? Okay, put this away. Get a ruler out and your notes, please. So today is the 20th. We are still in 3.7, so 3.7 continued. Graph linear functions. All right, what I want to focus on today is something called families. I forgot how to spell family all of a sudden. Families of functions. Families of functions. All right, so what this means is these are a group of functions with similar characteristics. All right. That might mean, well, what they mean is that the equation, the functions are the same form. For example, functions in the form of y equals mx plus b. These are a family of linear functions. Alright, you have not done these yet. Alright, but I wanted to introduce this. There are things called exponential functions. That's y is equal a times b to the x power. So any equation, any function in this form, any functions in this form are a family of functions. Alright, these would be considered a family of exponential functions. Because that's an exponential function. Now, we're not doing exponential functions today, but I wanted you to understand that from a variety of standpoint, I don't want us just focusing on linear equations, because they can be quadratic equations, it could be, exponential equations. All right, so any equation that's in the format y is equal to mx plus b is considered a family of linear functions. Are you guys cool so far? Okay. There's something called a parent function. We're going to deal just with linear functions. So a parent linear function, what this is the most basic linear function. In the family. It's the most basic. It's f of x is equal to x.
Teachers and students, please pardon the interruption. I'd like to thank all the students that donated to the Lighthouse as we filled up a whole conversion van, and the Lighthouse was thrilled for all your donations, so thank you to all the students that donated and those students that loaded up the truck. We do have Adrian Fernandez to do our end of the day prayer. Thank you.
In the name of the Father, Son, Holy Spirit. Amen. Dear God, please help each of us to make a bigger effort to help those who are in need. Thank you for the wonderful community, students, and all of the staff. Help our school to be blessed with your wisdom, kindness, and action. Thank you for making this school a better place. All things are possible with our Lord and Savior. In the name of the Father, Son, Holy Spirit. Amen. Thank you, Lord, for your
Great job, Adrian. Have a wonderful rest of your Wednesday. Thank you.
Alright, so if I put 0 in, I just get 0. If I put 1 in, I get 1. If I put 2 in, I get 2. Alright, so if I was to graph this, and that parent function does not change. That is always the parent function for a linear equation. So essentially, it's a direct variation equation that looks like that. Now, what I want us to do is, all right, I want us to kind of look at, different, and I get different colors out, so if you have like 2 different color pens or pencils beyond your pencil, I want you to use it, because we're going to graph the parent function and two other functions on the same graph. All right, we're just going to make one table for all of it. All right, so I want you to graph on the same graph f of x is equal to x, f of x, let's do g of x equals x plus 3, and then h of x is equal to 2x. So, why don't we create this table? Let's have our f. Let's do a column for f of x. Let's do a column for g of x. And let's do a column for h of x. All right, so we already know, let's use 0, 1, and 2. We already know we have 0, 1, and 2 for our f of x because we just did it. All right, our g of x, we need to do. So g of 0 is going to be equal to 0 plus 3. So go ahead and start doing this. Thank you. And we're going to see what happens when I take my parent function and I add a constant to it, and what happens to my parent function when I change my slope. All right, so indicate once you've done that, indicate on your table what color. That's what I would recommend. What color each of these are going to be on your graph, just so we can go back to it. It's not going to be a big graph, so I'm going to explain some stuff underneath it. Once you're done with this, what I'm going to be asking you to do is make some observations as to what happened to our graph when we, oh shoot, I'm going to have to adjust this. What happened to our graph when we made those changes? All right, so there are my three graphs on the same graph. Questions so far? How many of you guys are good with your graphing? Who's still graphing? Okay, go ahead and finish up. So we need to talk about this. What happened to our graph when we had when we left the x the way it is, but we added 3 to it? What happened to our graph? Just explain the difference between my pencil and my pink. What happened when we had g of x is equal to x plus 3? Seamus? Yeah, so we have the same slope, but the line moved higher, right? What direction is that? Is that vertical or is that horizontal? Yeah, this is called a vertical translation. This could have been x minus 3. It's the same thing. We have the same slope. Our line shifts up or down. So I'm going to put here line shifts up or down. Which makes sense, right? It's just my y-intercept that's changing, right? How many of you guys noticed that? All right, my slope stayed the same. How about my h of x was 2x? What happened to that? So that's my green one compared to my pencil one. Joseph? So I have same y-intercept, but the slope changed. All right, if you noticed here, we're going to talk a little bit about this slope change. This is going to be called a vertical stretch. I'm going to put in parentheses shrink. And I'm going to tell you the difference between those. You're going to try and tell me the difference between those. This one is a vertical stretch. But we could have a vertical shrink. And I'm going to put this on my next page so I summarize that vertical stretch or shrink differently. What do you notice about my slope of h of x in comparison to my parent slope? What do you notice about my slope here with h of x in relation to my parent slope, which is just this? What's the difference between these two? What's my slope here? What's my slope here? Come on, this is an easy question. What's my slope here? What's my slope here? Giselle? Okay, that's considered a stretch. All right, so when we talk about a vertical stretch, that's when my slope is greater than 1. All right, what do you suppose would be the case if I said a vertical shrink? And I'm going to say the absolute, let me think about this for a second. No, we're good. All right, how about a vertical shrink? What do you suppose is the case for that? Rafaela? It's less than 1, but it's bigger than 0. So it's going to be between 0. It's going to be between 0 and 1. Now that's when we have something like this. I'm going to go ahead and just do this really quick one. That's when we have something like, I'm not doing a very good job of this. So if here is my graph, here's my parent function, here is my vertical shrink, or vertical stretch. Here would be my vertical shrink. So that is a stretch, that is a shrink. But the other way that I could do this is that if my slope was less than -1, would still be considered a vertical stretch, or my slope is between -1 and 0. This is also considered a shrink. All right, but that's going to look something like this. So here is my here is my parent function. All right, that's going to look something like this, where my slope is negative. Either that or that. Here is my shrink, here is my stretch. Can you see the difference between those? The pitch of my line is steeper when I'm higher than 1 or less than negative 1, right? It's flatter when our slope is a fraction. All right, when my slope is a fraction, it's a shrink. When my slope is an integer, greater than 1 or less than negative 1, it's a stretch. You guys cool with this? Kind of? All right, you're playing with this tonight. You guys can go.